So far, we've looked at consistent systems versus inconsistent systems. We've seen that consistent systems have solutions that satisfy both equations, while inconsistent systems do not have solutions that satisfy both equations. We've also looked at independent versus dependent solutions and seen that independent solutions is when we have exactly one solution, and we have dependent solutions when we have infinitely many solutions. What we're going to look at now is how do we properly express the solution sets for each type of system? How does it actually look, or what does a solution set for each type of system consist of? When we're looking at the independent systems, we have exactly one solution that can be written as an ordered pair, x, y. Because there's only one solution, this is considered unique. In mathematics, unique is a word that we use to express that there's only one thing that exists. For example, a square is considered a unique shape because that's the only shape where all sides are congruent and all angles are right. Here, we have a unique solution because there's only one ordered pair that will exist and satisfy both equations. Because of that, we have a few different ways to write the solution set. And actually, there's more ways than this, but we're just trying to stick with the basics. So for example, in our in our graph display up here, if this intersection was the ordered pair 2, 3, we could write the solution set as just the ordered pair 2, 3. We could say when x equals 2, y equals 3. Or we could use this notation down here. These braces represent that we're looking at a set. In mathematics, we always have a solution set. And it just indicates that this ordered pair that we're writing is not some random ordered pair, that it is a solution for a system or some type of thing that we're looking at. So the braces, again, just indicate that we're looking at a solution. So we could just put the braces around it, and we would have one element in this set, and that's the ordered pair 2, 3. Notice here that when x is 2, y is always 3. If y was 3, x would be 2. That's part of the reason we're saying that it's independent, an independent solution. This is the one solution that satisfies both lines. Consider this versus a dependent system. So dependent systems have infinitely many solutions. We can't define a specific x and y value that uniquely satisfies all equations in the system. Now, while there are infinitely many solutions that satisfy all equations in the system, we can't define a unique, only one value that satisfies it. So for example, in our previous example, we had that one ordered pair. We can put numbers to it and say 2, 3, this is our solution, that's it. Here, we can't define one specific solution that satisfies the system. As a result, we understand within the solution set, one object is dependent on the other object. And so that's where we get this verbiage of a dependent solution. One solution is dependent on the other. And you can see this right here where we have the ordered pair written, but it's not written with numbers, right? It's written with algebra. And so we end up seeing we would define this as a dependent system. So let's say hypothetically, this system was the equation y equals 2x plus 5, right? That's one of the ways. It's two lines, so I could have it written multiple ways. I've just made up an equation here. So if this was one of the equations for the two lines, okay, then here are the possible solutions we could have. So we could have the solution set written in terms of x. So this is written as an ordered pair. We have for any x value, we know that y is equal to 2x plus 5. It's already solved for us up here. So this is a way to represent the solution set for this system. For any x value, y is dependent on x. It's expressed as 2x plus 5. So you see where we're getting that dependent language from. In terms of y, we see if I had solved this equation, I would subtract 5 and divide by 2 everywhere. I could have, this is what my x coordinate would look like, y minus 5 over 2, for any y value in the system. Again, now x would be dependent on y if we had solved this equation up here for x. There's two other ways. You see the braces again that we can write it, and this again is called set notation. The way we read this is for any ordered pair xy, or we're representing any ordered pair xy, this line right here is read as such that y is equal to 2x plus 5. It means that any ordered pair that creates this statement is a solution for the system of equations. And it doesn't have to be written in slope-intercept form. Okay, I just translated it down here into standard form. It could be written in any form. It doesn't even have to be one of the main linear forms, you know. It could be point slope form. It could be some other form of a linear equation. And as long as it's written with this notation, this is another way to represent the solution set for the system. And again, it has to be done algebraically because we don't have that one unique solution. We have a scenario where one ordered pair is completely dependent on another, and it's a set of solutions, an infinite set, and so we can only represent that algebraically. Finally, when we look at inconsistent systems, a lot of times students associate no solution and this symbol, and they do mean the same thing, but really in mathematics, this symbol represents, we call it the null set or the empty set. And it does, in layman's terms, mean no solution. We read it as no solution, similar to the all real number symbol. But here, it represents that there's no element, there's no ordered pair at all that would satisfy the equations. And you can see another way to write it is with the braces, and you don't put anything in the middle of them, again, because there's no element, there's no ordered pair that would satisfy or make the system true. So the three types of solution sets for systems are the unique solution, we looked at back here, where it's just one solution and we list the ordered pair. We can have the dependent solution. When we have that, we have options. The solution set can be written as an ordered pair, but one value is dependent on another. Or you can write it using this notation down here where you're defining any ordered pair, any xy, such that it satisfies the equation. And then we can write, and then we have no solution, and really that means a null set or empty set, that there's no element, there's no thing, there's no ordered pair that would satisfy the system of equations.